Wanted to work through an example of calculating the electrical potential energy of a arrangement assembly of point charges for a couple of special cases. The two cases are a triangular arrangement of 3 charges and a square arrangement of 4 charges. So I pictured those arrangements over here on the left-hand side. Here's the triangle upstairs. Here's the square downstairs. In particular, for the triangle, I'm going to imagine a equilateral triangle, equal sides triangle, and the charges are located at the corners of the triangle, and the charges are all the same size and same sign. And I've just labeled them by plus Q, and I've labeled the separations along the sides of the triangle. I've labeled those as A. So that's one case. The second case is the rectangular arrangement of the charges. In this particular case, I picked an arrangement in which the charges all have the same size, but it's a combination of 2 positive charges and 2 negative charges. So in the top left corner, bottom right corner are 2 positive charges. In the bottom left, top right are 2 negative charges. This is the arrangement of a little sodium iodide crystal. And the separations between the charges along the sides of the square are all equal. They're also all equal to A. So that's the second arrangement. So we're going to solve what is the stored electrical energy of this triangular arrangement, 3 charges plus Q. What is the stored electrical energy of this arrangement downstairs here of 4 charges, 2 positive, 2 negative, with these separations A. We're going to solve this problem using a single equation that represents the electrical energy of a pair of point charges and some arguments about symmetry or geometry. We're going to put those 2 things together, and we'll discover that we can rather quickly solve the electrical energy of the triangular arrangement and the square arrangement. The equation I'm going to use is this equation over here on the top right. So this is an equation for the potential energy of a pair of point charges, and they're labeled in this equation Q1 and Q2, and their separation, how far they are apart, is labeled R. So their potential energy for this isolated pair of point charges is the Coulomb constant, K, times the product of the charges, Q1, Q2, divided by the separation of the charges. It's as simple and straightforward as that. This equation can be proved, established, by actually assembling the arrangement of 2 charges. So you could imagine assembling 2 charges on your benchtop by bringing in 1 charge from far away, placing it on the benchtop, bringing in the second charge from far away, placing it on the benchtop. If you took track of all the work you had to do against the electrical force to bring the 2 charges in, bringing in the first charge actually costs you no work because there's no other charges around. Bringing in the second charge does cost you some work because there's the first charge around. If you track all that amount of work that you do bringing in the charge, remembering that work is just transfer of energy, so tracking the amount of work you do is tracking the amount of energy you put in to assembling the charge distribution, you come up with, you arrive at this formula. This formula for the energy stored by a pair of point charges. We're going to apply this formula for the energy of a pair of point charges to the triangle arrangement, to the square arrangement, by applying it to every unique pair in the triangular arrangement of charges and every unique pair in the square arrangement of charges. So to apply the formula, we've just got to look at the triangular arrangement, figure out how many unique pairs there are in that triangular arrangement, unique pairs of charges in the triangular arrangement, and then apply the equation to each of those pairs and total up the amount of electrical potential energy stored by the unique pairs. And then we do the same thing for the square arrangement. We've got to look at the square arrangement. We've got to figure out how many unique pairs of charges there are in the square arrangement. And then we'll just apply the formula to find the electrical energy of all the unique pairs, and then we'll just add them all up. So it's a rather simple and straightforward application of the formula for the energy of a pair, but it does require us to identify the unique pairs in the two different arrangements, the square arrangement and the triangular arrangement. Let's start with the triangle, and we'll move on to the square. Triangles are a little bit simpler because there's a smaller number of pairs. Squares are a little bit more complicated because there's a greater number of pairs. The triangle is also simpler because of the fact that we'll discover the pairs are all involve the same charges and all involve the same distances, where in the square we'll discover that some pairs have different separations and some pairs have different combinations of positive and negative charges. So for the triangle, here's an example of one pair. The top and left-hand charges are a pair in the triangle, and we can apply the equation for the electrical potential energy of a pair to that particular pair. And so the electrical potential energy of that particular pair would be K, the Coulomb constant, times the product of the charges. Well, it's a plus Q and a plus Q, so it's just going to be a Q squared, a positive Q squared, and divided by the separation between the two charges. That's just going to be this separation that we named or labeled A. And so that's the electrical potential energy of this particular pair. And then we could ask, well, what are the other pairs? Well, I can see two other pairs, two other unique pairs. There's this pair here that involves the top charge again and the bottom right charge. And then there's a third pair, which involves the left-hand charge and the right-hand charge. So there's two more pairs here. And this is the total number of unique pairs in this triangular arrangement. There are 3 of them. And so identifying those 3 pairs, we can just go ahead and add up the electrical potential energies of the 3 pairs. We've already got the first one. That was over here on the left-hand side, the top charge and the bottom left charge. There's 2 more. But if we look at those 2 additional pairs, you'll notice that they both involve the same amount of charge as the first pair, a plus Q and a plus Q. They both involve charges separated by the same distance as the first pair. That's the distance A. And so they all have, the remaining 2 pairs have electrical potential energies that are also K, Q squared, the product of the 2 charges, over A. And so this electrical energy here is the electrical energy of the first pair that we talked about, this pair here, but it's also the electrical energy of the second pair we talked about, and the third pair, the horizontal pair that we talked about. And so the total energy of the triangular arrangement will just be 3 times this. And so that is the potential energy of the arrangement of 3 charges. Let me make a remark before we move on from the triangle to the square about the counting of the number of pairs, the number of unique pairs, because there was 3 in this triangle and we counted them up. But let me be a little bit formal, more formal, about how we might count up the number of pairs, because that's going to be important for the square, where it might be a little less obvious how many pairs there are. It wasn't so important for the triangle, where I think it's obvious that the triangle has these 3 pairs. Let me show you one way you could imagine counting up, rigorously counting up the number of pairs. Start with a particular charge. Let's start with this one downstairs here. If we start with this one down here, how many pairs are there, unique pairs, that interact with this charge, that involve this charge? Well, look, it's obvious that there is two pairs. There's this pair that involves the top charge and this pair that involves the right-hand charge. So there's two pairs interacting with this first charge that we picked. And so let me just write down that. I've identified two pairs. Let's move on to a second charge and ask how many additional unique pairs there are interacting with that second charge. I picked this one downstairs here on the bottom right. Well, I can see two pairs that involve this one on the bottom right. There's the pair with the one upstairs here, and there's the pair with the one on the right. The one with the pair upstairs is a new pair. It's a new unique pair that we haven't discussed before. But the one at the bottom here, this pair, we already counted this pair when we looked at the pairs involved with charge number 1. And so of the two pairs involving this charge over here on the right-hand side, only one of them is a new unique pair. It's this one here. One of them was already counted. It's not a unique pair. And so I'm going to just, as I think about this bottom right charge, I'm just going to add, there's one more unique pair that we've identified. Let's go up to the remaining charge. This remaining charge upstairs here also interacts with two other charges. So there's two pairs here. There's a pair with the bottom left and a pair with the bottom right. But are these unique? No, we've already counted this pair here when we were thinking about the first charge on the left-hand side. And actually, we've already just counted this pair here when we were thinking about the second charge on the right-hand side. So when we think about the third charge, all its interactions with other pairs involve pairs that we've already counted. So there's no further unique pairs when we think about this third charge here. So I would be adding 0 unique pairs from that charge. If I add all these numbers up, how many unique pairs we found with the first charge where we started on the left, the second charge when we started on the right, the third charge when we thought about the charge upstairs here, we got 2 plus 1 plus 0, which equals 3. So this is a formal way of coming up with the 3 pairs of the triangle. And this might be handy, and this pattern might be handy, that when you have 3 charges, if you start thinking about the first one, there's 2 interactions. The second one, there's 1 interaction. And finally, the third one, there's no more unique interactions. This pattern here is kind of handy for calculating the number of interactions for the square. Okay, let's go ahead and count up how many pairs there are for the square. How many unique pairs of interacting charges there are for the square. We're going to do that first because then we can go on and apply what is the potential energy of an individual pair and add up all the potential energies of the individual pairs to get the total potential energy of the square. Our job here really is to figure out how many pairs there are and what charges and separations of charges are involved in those pairs for the square. So again, I'm going to pick a particular charge. I'll pick this one on the bottom left again to start at and figure out how many unique pairs that charge interacts with. And it's pretty obvious. There's one upstairs here. That's a unique pair. There's one over here on the right. That's a unique pair. And there's one over here on the opposite corner. That's the third unique pair for that first charge here. And so I'm going to write down how many unique pairs there are of interactions for that bottom left-hand charge. It's 3. Now, an interesting point here is that 2 of these, the interaction with the top left-hand charge and the bottom right-hand charge, involve interactions with opposite charges, so it's a minus q and a plus q, and involve interactions between charges separated by a distance a. The third pair in our unique pairs of interactions is the interaction between this bottom left negative charge and this top right negative charge. So it's an interaction between two like charges, and they're actually separated by a greater distance. This distance between opposite corners by trigonometry it's not a, it's bigger than a, obviously. It's the square root of 2 times a by Pythagoras' theorem. So these are the number of pairs, but there's two distinct pairs in there. There's the one between the neighboring charges on the sides of the rectangle square, and then there's a interaction with a opposite charge on the opposite corner of the square. And so we're going to have to be cognizant of spotting those two types of pairs with opposite corners and with adjacent sides. And let's move on to the second charge. So this charge interacts with the charge above it, the charge opposite it, and the charge downstairs here on the left-hand side that we've already discussed. So that's three interactions that charge has, but one of them we've already counted. So this is not a unique interaction. We already counted it in our number 3 of unique interactions over here. And so there's only two remaining interactions with between the two right-hand side charges and the opposite corners here, the top left and the bottom right, that are remaining unique pairs. So when I add up the additional unique pairs coming from the interactions of this bottom right charge, there's going to be 2 more. So I'll add that in. If you went up to this charge here, so let's call this the third charge we're going to think about. Well, it interacts with the bottom charge, but we've already counted that. It interacts with the opposite charge, but we've already counted that. The only interaction that it has that we haven't counted is this one between the top right charge and the top left charge. That's the only remaining unique interaction that we haven't counted, and so we're just going to add that 1 on there. And then finally, we could go to the fourth charge. This is the one on the top left now. But if we think about its interactions with the one on the bottom, the one on the right, and the one on the opposite corner, they've all been already included in this computation of the number of pairs in the rectangular arrangement of charges. And so there's no more unique pairs to add together here. The total number of unique pairs is then 3 plus 2 plus 1. That's 6. There are 6 pairs in there. Now, of those 6 pairs, 4 of them involve the interactions between charges that are along one side. So that here's 2 charges on the left-hand side. That's a pair of charges, opposite charges that are separated by A. Here's another example of that. Opposite charges separated by A on the right-hand side. And here's another example of that on top and on bottom. Opposite charges separated by A. So 4 out of the 6 are charges that are opposite, separated by A, being the unique pair. The remaining 2 are the 2 interactions involving the opposite corners. There's this pair of opposite corners here from the top left to the bottom right, and then there's this pair here from the bottom left to the top right. So 2 are opposite corners. They involve like charges, 2 plus q's or 2 minus q's. And they involve a greater separation. We said that was the square root of 2 times A by Pythagoras' theorem. So now our work is mostly done. The total potential energy of this rectangular arrangement of charges is, let's start with the 4 charges, 4 pairs that are between kind of nearest neighbors, is what I would call them, that are separated by just the side. There are 4 pairs that involve charges along one side, the left-hand side, right-hand side, top side, or the bottom side. Their electrical energy for each pair is the product of their charges. So that's going to be Q squared times the Coulomb constant divided by the separation A. And this is a negative contribution to the electrical energy because one charge is negative and one charge is positive. So I put the minus sign here. So that's the contribution from the charges that are nearest to one another, separated by a distance A. And then there's a additional contribution from two pairs across the opposite corners. And that's going to be, a positive contribution to the potential energy because these are like charges, either two pluses or two minuses. So plus times plus is plus, minus times minus is plus. These two contributions from these two pairs, the potential energy of each pair is K, the Coulomb times constant, times the product of the two charges. So this is going to be Q squared plus Q squared divided by the square of the distance between. The square of the distance between them is square root of 2A. And so these are the two contributions from the various charges, from the nearest neighbor charges and the opposite corner charges. And together they make up the 6 pairs that contribute 6 contributions to the total potential energy. If I wanted to simplify it a little bit, I could spot that there's a common factor K Q squared over A in each of these terms. And so I could actually rewrite this as minus 4, this piece here, plus 2 over root 2, which is just root 2, multiplying this common factor, K Q squared over A. And so that's the potential energy of this arrangement. And so we've solved here the potential energy of a triangular arrangement of equal charges and a square arrangement, like a crystal lattice of sodium chloride, of 2 positive charges and 2 negative charges. And we've done it with one equation, the equation for the electrical energy of a pair of charges, and then figuring out, and most of our work was figuring out how many pairs of charges there are and what are their separations and what are the values of the charges. Let me make one final comment about the result here. This was a positive electrical potential energy for the triangular arrangement. This, although there's positive and negative contributions, overall, minus 4 is bigger than square root of 2. This is a negative potential energy for the square arrangement. With the positive potential energy of the triangular arrangement, we had to push those charges together to get 3 like charges in the corners of the triangles. So they're kind of storing up electrical energy and they want to release it. They want to fly apart. For the square arrangement, on the other hand, these charges would have fallen together in this arrangement, assembled themselves in this arrangement. To pull that arrangement apart, we would have to do the reverse. We would have to add energy. We'd have to do work to pull these charges apart. So the top arrangement kind of wants to fly apart, whereas the bottom arrangement wants to stick and stay together. And that's the difference between the positive potential energy of an arrangement of charges and the negative potential energy of an arrangement of charges.